Hello everyone, welcome back to this session. And in this, I'm going to explain about the collective communication on OpenMP, and we'll clearly understand how processes communicate using broadcast, scatter, and gather. So we will also look at the simple code examples to make the concepts more crystal clear. So let us first understand what is this communication in parallel computing. In parallel computing, tasks are divided among the multiple processes that run on different processors or cores, while each process performs its own computation, and they often need to share the intermediate results, coordinate action, or combine outputs to solve the large problems. Since these processes may not share the same memory, especially in distributed systems, communication becomes essential. It allows the processes to exchange the data that is required for computation, coordinate execution, that is to maintain the correct order, synchronize results across the different processors. So communication can occur in a different forms, such as mass message passing, that is sending and receiving data between processes, collective communication, broadcasting or gathering data among many processes. Efficient communication is critical because poor communication can lead to delays and performance bottlenecks. So well-designed communication improves the scalability and speed. So communication is a fundamental aspect of parallel computing that enables multiple processes to collaborate process to collaborate effectively, that ensuring correct, efficient, and scalable execution of complex tasks. So what is MPI? The message passing interface, in short MPI, is a standardized and portable communication protocol used in parallel computing. It allows multiple processes running on different machines or processors to communicate by sending and receiving messages. In distributed memory systems, each process has its own local memory and they cannot directly access each other's data. So MPI solves this problem by providing functions to send data from one process to another, receive data from the other processes, coordinate and synchronize executions. And the key features of this message passing interface is works across the multiple nodes in a cluster, which supports both the point-to-point and collective communication. This is highly scalable for the largest systems and supercomputers, and language supports C, C++, Fortran. So why is MPI is important? So MPI enables efficient communication in distributed systems, so widely used in a high performance computing like HPC. So suitable for the applications requiring the large scale parallelism. Like suppose if you take an example scenario, in a cluster computing setup, one process can send computed results to another process using MPI functions like MPI send and MPI receive. So MPI is a powerful standard that enables the efficient and scalable communication between processes, making it a cornerstone of modern parallel and distributed computing systems. So what is a collective communication? Collective communication in MPI, collective communication refers to the communication operation that involves all the processes within a communicator, that is nothing but a group of processes. Instead of writing multiple send and receive calls between individual processes, MPI provides a predefined functions that handle the communication for the entire group efficiently. If you look at the key characteristics of this collective communication, all processes participate in the operation. So it simplifies the communication compared to the point-to-point messaging, optimized for the performance and scalability, which also reduce the coding complexity. And if you look at the common collective operations, or like broadcast, scatter, gather, reduce. Broadcast, that is one process sends data to the all processes, whereas the scatter distribute the parts of the data to the all processes, gather, that collect the data from all processes to one, and reduce is combines the data like sum, minimum, maximum, etc. from all the processes. So why we use this collective communication? So to avoid writing complex send and receive, send or the receive logic, so that ensures the efficient data sharing across processes. It improves the performance in parallel applications. These are the reasons why we use this collective communication. So the collective communication in a message passing interface, MPI, provides a powerful and effective, efficient way for processes to communicate as a group. So that makes the parallel programs simpler, faster, and more scalable. Let us see here the types of communications. In MPI, collective communication and several operations exist, but this so in MPI collective communication, several operations exist, but this session focuses on three fundamental and widely used operations that perform the basis of data exchange in parallel programs. The first one is a broadcast, which sends data from one process, that is a root process, to all other processes. So that ensures every process receives the same information. This is mainly useful for sharing common inputs or configuration data. Next one is a scatter, and this distributes the different portions of data from one process to all processes. So each process receives a unique subset of the data. This is mainly ideal for dividing the work among processes. Next, gather. This collects the data from all processes and sends it to a single process, that is a root. So combines the results into one place. This is mainly useful for collecting the final outputs. So these three operations, broadcast, scatter, and gather, are essential building blocks for efficient group communication, enabling smooth data distribution and collection in parallel computing systems. So let us look deeper of about each category here. Like first one is the broadcast, and this broadcast in OpenMP is a collective communication operation where one process, that is the root, distribute the same data to all other processes in the communicator. So let us see how it works. One process is designated as the root, and the root holds the initial data. MPI automatically sends this data to every other process. So all processes receive an identical copy. And if you and the main key features of this broadcast is efficient to one-to-all communication. It eliminates the need for multiple send operations, which ensures the data consistency across all processes. For example, if a configuration parameter at the data set needs to be shared with all processes before computation, the root process can use the broadcast to distribute it efficiently. So broadcast is a simple and powerful MPI operation that enables the fast and consistent data sharing from one process to all others. So that forms a foundation for many parallel applications. And this is the syntax of how the broadcast. Here the data is sent from the root process to all the processes in the communicator. For example, if process 0 sends the value 100, all other process will receive the same value. And then one is a scatter concept here. And this scatter, here the root process holds the full data, and MPI automatically distributes equal chunks to each process. So let us compare MPI collective operations like broadcast send the data to all, scatter divides the data among processes, gather collects data from all processes. And like if you like broadcast, this is mainly used for one to all, that is a single root process sends the same data to all other processes. And if you take a scatter example, here the arrays are divided among the processes. So next, gather, where all the processes send the data to the root. And I'm going to explain one simple example of how this gather and mainly the reduction would be done with the help of the multiple threads. And next one is a gather function. If you look at this MPI gather function, and this is a send buffer, these are the different parameters inside this function. Send buffer, send count, data type, a receive buffer, and receive count. This is at the receiver side, these are at the sender side. The data type and root is always the main node, MPI communication world, and this is for communication. And next one is and gather, and the results collected into one array. Like suppose let us, I just want to pass this example to the next. And if you compare this broadcast, these are the three main MPI communication communication routines, like a broadcast. So broadcasting means was sending one to all, the same message would be sent to all the processes. And the scatter is dividing, like suppose if uh, let us take one simple example as a data set, and the data set would be divided into the blocks, and blocks, each block would be all the divided blocks are distributed across the nodes in a cluster. So that is how the scatter would be. And next one is a gather, collect the data. That is like suppose it is completely opposite to this scatter. So scatter like dividing and distributing across the nodes, whereas a gather is to collect all the different pieces and collect into the single entity. So these are the just a quick comparison against these three collective communication routines, because the point-to-point communication is very simplest communication. And if you look at the advantages of this MPI, this collective communication routines, and these are mainly for efficient communication and simplifies the coding. There is no much coding required. And if you look at the disadvantages of this collective communication is synchronization overhead and communication cost. And if you look at the applications where this collective communication would be used, like a serial, that is a point-to-point communication, that is a simple, that is not used, that is used in a serial. But whereas this collective communication, so that is one best example is a parallel sorting. and matrix operation, like suppose if there is a complex matrix, and if you want to make it more faster, so then we can divide the matrix, and so that we can do this operations in parallel, so that it would be completed in very less time. And also the scientific computing applications. And if you take a real world example, like distributed databases and AI training systems are the examples of this, where we use this collective communication. So collective communication improves the efficiency. This is essential in MPI programming. So okay, and before we move on to this coding part related to this OpenMP, that is collective communication related code. So let us try to understand, because the same numerical problem I'm going to solve using this OpenMPI, so that you'll get much clarity here. This is a parallel sum calculation with the MPI, that is a collective communication routines like reduction mainly. And here the task is to calculate the sum of numbers from 0 to 100. So that is like 0 plus 1 plus 2 and so on, so plus 100. So we'll start, and that is with the 0 to 100 range, and this is the ending value. So starting, and this is the range. So now, and let us assume that if there are four processes are there, so like process 0, it is obviously the master process, and process 1, 2 and 3. And this, if you look at the ranks of these processes, always a master process rank always 0, and then remaining process, this is rank 1, rank 2, rank 3, etc. So now the task is to find out the sum of an 100 natural numbers. So if these four processes are involved in this parallel processing, and also the static the open loop scheduling approach, so then, and these this would be divided among these four processes. So here you can see how it would be divided, like a range 0 to 24 numbers would be divided, and that is assigned to this process 0, and next range is 25 to 49, and that is assigned to the process 1, then 50 to 74, and then 75 to 100, that is the last range of numbers given to this process 3. So now, and this process 0, like each process is going to calculate the partial sums, that is by adding the uh, numbers given, the range of numbers given to that particular process. Like for example 0 to 24, that is nothing but a sum of 24 natural numbers, like 0 plus 1, 2 plus, and so on, 24. And similarly process 1, 2 and 3 also calculate the partial sums like this, partial process 0, 300, and 925, 1550, and double to 75, that is the process 3 partial sum. So now, and this is, we have distributed, we have split the range like 0 to 100 into the four pieces, and we have distributed among the processes, and this is called as a scatter. Next one, once all the process complete their partial sums, calculation of a partial sums, and we are performing this. So this is also reduction, like because this is the way we can, because these are the four partial sums. In order to get the final sum, we have to reduce it. So now in this, there will be a communication happens between the processes. That is, the master process also involved in this task. So it also performed, that is the task to calculate the partial sum, that is range from 0 to 24. So now it will receive the remaining, it will receive message that is related to the partial sum from the remaining processes, like process 1, 2, 3. Like from process 1 it received 925, that is a partial sum, and process 2 received a 1550, and then process 3 2275. Then it will perform this, and it reduces and for produce the final sum. So this is the example I'm going to explain in this coding part also, and some few other simple, like hello world using the OpenMPI send and receive, how routines would look like. So now let us move on to this Google Colab. So let us first connect to the runtime environment. Okay, so this is, meanwhile, let us understand the code here. Parallel hello world program. Here you can see here MPI init, MPI communication, the rank, MPI communication size, and this is just only printing the hello world message, and by which the process, and the size also would be mentioned here. Next one is of MPI finalize. This MPI initialize, that is to initialize, create the environment, communication environment, and this routine MPI finalize to clean up the MPI environment. So, and then the communication happens in between these two phases, like MPI communication rank, and this communication, and the rank, like get the rank, that is ID of the processes, and this one is the size, get the total number of processes by using this function. Next, to print this hello world message, because the master process will send a message so that the rest of all the process would receive it. And then, so let us, now we have connected this, so let us run this code. So by using this MPI cc hello world, because it here it, this, I think there's a message like running a as a root is strongly discouraged as a mistake example defining. So for this, you can see here. So now, and to avoid this kind of a warnings or messages, like we can use this allow run as a root user, because here it has mentioned like running as a root is a strongly discouraged, because it due to the security issues strongly discouraged here. So for that, to this we use this option, so allow run as a root option. Next, we use the oversubscribe, like by default if you look at this, like number of processes 2. So if you want create a logical, like a number of logical processes to see, like to get a more clarity, then we use this oversubscribe option, so that we can create this option by using 6 process we can create here -n, and this is the 6 number of processes, and this is the file that is need to be run. So that's why we'll get it. Otherwise, suppose if I just set its number as a 4, so only the 4 process would be. Now hello from the message process 1 of 4, like this. The next MPI send and receive routines you will understand here, and this character message initialize, and this MPI init get the number of processes, and the process rank if the size is not equal to 2, that is if the rank, okay, that is to check whether the process is a parent master process or not. If the rank is 0, that means run with the two process only. Else if the rank equal to 0, so string copy and then print, because who is allowed to send a message, because always the master process is allowed to send a message. So that is we can control by checking the rank of a process. If else if the rank equal to 1, then that should be a receiving process, like MPI underscore receive. This is a receive routine, MPI receive routine. Whereas this one, because here the process we are verifying is MPI, that is by using the rank equal to 0 means that is a master process. So master process is allowed to send the message, and then we'll send the rest of the processes. That is so here the rank is equal to 1 for the rest of the processes, because here only the two process, that's why we are just checking the rank 0 and 1 only directly. Otherwise if there are a number of process, so only this rank for the master equal to 0, then remaining the not equal to 0, so all the integer values. So then this is to clean up the environment. So let us run this. So you can run and just to see that master is sending message, worker received hello from the master process. This is how communication happens in this MPI. And let us see another example here. These are all like there are two processes. Like suppose if the master process, if a rank equal to 0, integer value, like these are the three values. So MPI send and the print master finished, and then you check this rank 1, that is for process 1, rank 2 to process 2, rank 3, that is to confirm the process 3, and then finalize MPI. So that is another example here. These are the non-blocking, but whatever the numerical example I explained, I just want to show that how that was implemented. Yeah, so this is a sum any source, and this is we define the start 0 and end equal to 101. So integer main, and this is the main function, rank and size, and we have to initialize this MPI init and get the rank, that is a process ID, and size, number of processes. So MPI communication rank and size, we will get it. Next, calculate the start and end points by evenly dividing the range, because the if we want to find out the sum of 100 natural numbers or 200, 201, or whatever it is, so how we are going to divide the range, that is defined here. Integer start equal to n minus start by size into rank, that is number of process. Based on that, it would be decided the last process, like the remaining all process would get a even equal number of that is the elements. But whereas the last process, if it is an odd number, that gets one number extra, that is the rest of all the values would be assigned to the last process. So the last process needs to do all the remaining ones here, like you can see rank equal to then size minus 1, then end. So do the calculation, that is to for each range we have to, like each process need to calculate its a partial sum. So for that, this function, this block of code, and this is just debugging the output, like a process and the sum and the range and the starting ending and some value. And the communication process 0 receives the everyone else sum, that is to get the confirmation, and then parent process receives each partial sum and add it to ours. Now like this, all the confirmation messages would be printed. There is nothing complex in this code here. So the only the thing is you need to understand this, a partial one, MPI init, MPI any source, or all these are only the things, what are the parameters used in this MPI send and receive, and the rest are all like same, like normal code. And this is to clean up the environment here. So now let us run this. So now you can see here process 0, that is the range is 0 to 24. Its initial sum equal to 300. Process 0 got the data from the process 1 and process 0 got data from the process 3. Okay, this is the next process 1 send the partial sum that is from the range 25 to 49, that is 925. And then process 3 also finished calculating the uh, partial sum that is for the range from 75 to 101. And then process 0 got the data from the process 2, like you can see here in between, because these are the very simple calculations, like this is done very faster. So that's immediately process 0 got the data from the process 1 and process 3. And then process 1 and 3, this is just a printing the message, and process 0 got data from the process 2 also, and the process 2, then final sum is calculated as 1515. So that is the way you can the same function here. And this is a broadcast example. So if you look at this is just to create a MPI communication environment, and this is trying to get the rank and size and the the character string process 0 read in a string. If rank equal to 0, then string copy hello MPI. And now the broadcast this out to all the processes. So MPI broadcast. So this message will be broadcasted from the process 0 and print the string and finalize it. So now you can, if you run this is a very simple code, but if you once you understand the theory, it is very easy. So now you can see here broadcasting process 0 has hello MPI 1 2 3 4, all the remaining all the process have received the message from the master process. So that's it. Thank you for watching.